Okay, so welcome everyone for this first webinar on the INRAE stream gauging rulers that we have developed in the recent years. And the objective of today's session was to demonstrate the ruler to those who don't know it and to have some exchange with those who already use it, to have some feedback from the users, and also to share some news and new evolutions of the tool. So today I'm glad to be presenting with my colleagues. So Michael and I are working with INRAE, a public research institute in France. And Cédric Guino is working with Catercom. So Catercom is an association, a technical association that provides services, information, and support to river boards and other water stakeholders in Normandy. It's based in Normandy in the northwest of France. And Adrien Vergne, who will join us a bit later, is working for the National Hydrological Service of France, based in the regional office of Brittany in the very west of France, in Rennes. So this presentation will have three sections, three parts. I will present the first part about the ruler itself, how it works, and what are the main news and evolutions of the tool. Then we'll have a break for questions and answers, but feel free to write any questions or comments you have in the chat, and my colleagues will answer you, and we can have further discussion during the break. And then the second part will be presented by Cédric about the smartphone tool Courage he developed for the field measurements using the ruler. And then we'll have a question and answer session again. And a third part by Adrien about a nice partnership they have set up between a professional hydrological service, his service, and a river board that wished to measure the low flows of a non-monitored stream in their region. So the tool has different names, even if it's the same ruler. We have some French names, and we proposed the name stream gauging ruler because it's basically a big plastic ruler or board used to measure discharge in the streams. But in the literature, it was also named velocity head rod or transparent velocity head rod or stream velocity board, for instance, and some other nicknames. But we'll stick to the stream gauging ruler name for this presentation. So first, basically, we may wish to measure only flow velocity with the ruler, but usually users want to measure stream flow or river discharge, which we have to define. So discharge is the volume of water passing through a cross-section of a stream during a unit of time. So basically, discharge can be seen as a volume of water divided by the time of flowing, and the units will be cubic meters per second or liters per second for smaller flows. There are also other units, but let's stick to SI units, metric units. Equivalently, we can see the discharge as a flow velocity times the weighted area of the cross-section. So this product also yields cubic meters per second. And then this is an illustration of the velocity distribution throughout a river cross-section. This one is a very big one. It's in the Amazon River. So it's a very big cross-section, but we would have the same type of thing in smaller streams. And this is the basis, sorry, for discharge measurement using the stream gauging ruler, typically. So we'll measure velocity, we'll measure depth and width and area, and take the product to compute discharge. So this method is not specific to the stream gauging ruler. It's actually the method that is used with current meters, any type of current meter. It's called the midsection method. Basically, we'll measure across the river at several positions, x1, x2, x3, etc. We'll measure the flow depth and the velocity perpendicular to the transect. So to compute discharge, we need that component of velocity that is perpendicular to the cross section. And we need to get the depth averaged velocity. Then, knowing that velocity, we need to know the area that must be multiplied by this velocity. We'll use the positions of the verticals to compute the width of this kind of rectangular panel around each measuring vertical, and multiplying this width by the depth of the vertical will get the area of all the rectangles here, the rectangular panels. Then multiplying the velocity, remember the perpendicular velocity, with the area of each panel will provide us with the discharge or the partial discharge around each vertical. And then we just take the sum of all these partial discharges to get the total discharge. So that's the basic principle of this discharge measuring method. There is some tricks, and the main trick is how to compute the discharge near the banks or the edges of the cross section. With the ruler, we apply a very common procedure. We use an edge coefficient, Ke, to extrapolate the velocity profile from the last vertical, the nearest vertical, to the edge. So you'll see that with the ruler, we'll have to estimate this edge coefficient. And here you have typical values for different types of banks, either natural sloping banks, for instance, or smooth vertical banks, like when you are measuring close to a concrete wall in a canal, for instance. But then importantly, remember that we won't measure velocity at the edge of the water. And actually, we can't measure that velocity that we know that it's zero, actually. We'll only measure the flow depth near the bank. Okay, so now the main steps of that method, irrespective of the kind of current meter you would like to use, actually. So first step, we have to choose a proper site for the measurements. So typically, we need to have a relatively uniform geometry and flow upstream and downstream or cross-section. Typically in France, we usually advise to have these uniform conditions, at least one width of the stream downstream of the cross section and two width of the stream upstream of the cross section. Of course, in many occasions, we won't have these perfect conditions, but we try to have this as best as possible. And when using the stream gauging ruler, we won't be able to project the velocity component perpendicular to the transect because the ruler will measure the flow perpendicular to itself. So it's even more important to try to have a flow that is nearly perpendicular to the measuring transect over all the transect. So no oblique flows. Then second step, we have to set a tagline. So this type of ruler tape that we need to measure the positions or the abscissa across the river. And setting up this tagline is an occasion to explore the cross-section, to check with your boots and your eyes, to check that there are not big blocks, obstacles, big holes, and we can move some blocks if they disturb the flow, for instance. Then a very important step, we have to think about the number of verticals we want to measure and where to put them. It's very important actually to have a good description of the shape of the bottom and also of the shape of the velocity profile. And also it will be more advantageous to have more verticals where most of the discharge flows. Especially you see here, we have deep water and higher velocity here. So higher discharge will be in the center of this cross section. So it's better to have a smaller space between the verticals where the flow is more intense. So remember that the option of equally spaced verticals is not the best choice in many cases, unless you have a very uniform canal or very uniform cross-section and velocity profile. Okay, then we start the measurements now. We are ready to start. So first thing, we have to check if the water level changes during the measurement. So we first measure the initial water level, either using a staff gauge, if we have a staff gauge at our measuring site, or we can also use some temporary ruler to measure the height of the water or any vertical reference. It's just to check that the discharge is not changing too much during the time of the measurement. And then we note the date, time, and time zone of our discharge measurements, and we start. So first we start from the bank. So we have to measure the position, the abscissa, and the depth. And we note the type of the bank. That will be useful to estimate the H coefficient, as I already explained. So just remember that we don't measure the velocity at the H, just the depth. And then we start measuring the verticals. So we can measure verticals in any order and according to the plan at step 3. Then at each vertical, we will measure the velocity. So the velocity can be measured with a variety of current meters. Usually we have to align the current meter perpendicular to the tagline. Again, we measure the abscissa on the tagline, on the ruler, and the depth, usually using some graduated rod or sometimes with some pressure gauge as well. And then we close the measurement by measuring the arrival bank, then just measuring the depth and the type and abscissa. And we read again the water level just to check that it is similar to the initial water level. And that's it. So this procedure is the typical procedure we use for any current meter wading discharge measurement. Now we have to choose an instrument to measure the flow velocity. And there is a wide range of instruments that are, for most of them, quite expensive. So several thousands of euros typically for these mechanical current meters or propellers or acoustic Doppler current meters, isoacoustic instruments, electromagnetic current meters, and also profilers, ADCPs, can be used to apply the method I've just described. So station by station, either on a floating platform, like in this picture, or at the bottom of a wading rod. there are some instruments like this, but they are quite expensive. The floats, sorry, it's not translated from French, but floater is for floats. The floats is inexpensive, but not really easy to apply precisely. And the stream gauging ruler is about 200, 250 euros. So the first main advantage of this system is that it's low cost, but it's also low tech. So it's very sturdy. There is no electricity, no electronics, only mechanical parts, pieces. And it's quite easy to deploy compared to the other techniques and instruments. If you use current meters, typically we will have to measure a number of velocity points along each vertical, from 1 to 3 or more points. And we have to wait for a given exposure time in order to average the velocity fluctuations over time. So it's typically recommended to wait for 30 to 40 seconds. So if you compute the measuring time it takes, it's rather long. And ADCPs and any types of profilers are relatively touchy to deploy and relatively complex as measurement processes. So it requires some relatively high skills to use them. In contrast, the stream gauging rulers are really easy to deploy. And a very interesting feature is that we will measure directly the depth averaged velocity. So we have only one measurement to do at each vertical to get the depth average velocity that we need for computing discharge. Okay, now the stream gauging rulers or velocity head rods existed very long time before us. You have these examples in the literature from the 40s, the 60s. So it was a bit forgotten as a technique, but it was known. We didn't invent that system. But what happens is that Mark Fonstadt and co-workers in 2005 reactivated the interest for this system by proposing a transparent version and making some comparisons with other current meters and proposing an empirical rating for computing the velocity. So that was a very important first paper. And then Robin Pike in Canada and colleagues published another study in 2016 with a slightly different model, but also a slightly different rating for velocity measurements based on a very large number of comparison data. So we were interested in that system after these publications. Let me remind the velocity measurement principle of the system. It's a basic application of the Bernoulli theorem, or it's also similar to how pitot tubes work for measuring flow velocities. The principle is to convert kinetic energy of the flow upstream, so in relation with its velocity, its approach velocity, v1, by blocking the flow with an obstacle, which will be the ruler in our case. So the flow is blocked against the obstacle, the ruler, and then the velocity drops to 0, which converts the kinetic energy of the flow into potential energy, a bit like this kid's energy on the swing that is converted from kinetic energy when the swing is fast and low to potential energy when the swing gets higher and the velocity decreases to 0. So we get the maximum potential energy against the obstacle, and the Bernoulli theorem, Bernoulli equation, states that the hydraulic head is equal at the 2 points, 1 and 2, and then we get this theoretic velocity rating between the depth average velocity here, V1, and the height of the water surge against the obstacle, delta H, here. So the first velocity head rods worked or were operated using this theoretical rating. But actually what Mark Fonstadt and then Robin Pike showed is that in practice, we need a correction. So we started our work in 2018, and we also collected a number of comparison data with other velocity measurement techniques, both in the laboratory in a flume and also in the field, thanks to the cooperation of many field hydrologists in France. And you can see these data here. You can see the relation of the reference velocity and the velocity computed using Pike et al. Velocity rating, this equation here. And actually, we confirmed that this equation was accurate within, say, 1 or 2%. So we didn't want to introduce another equation, and we stick to this equation that is actually carved on the INRAE stream gauging rulers. If you have one, this equation is given in the plastic. And also we have also the same operating conditions as proposed by previous authors. So depth can extend from 5 centimeters to 70 centimeters due to the design of the system. When you measure in very shallow flows, it's possible, but you need to have a very flat and very homogeneous bed. Otherwise, the percent error in flow depth can be too high. But compared to other systems, the velocity head rod is able to measure in very, very shallow flows, much shallower than what current meters can do. And the velocity rating seems to be okay from 20 to 120 centimeters per second. For faster flows, actually, it can be difficult to hold and maintain the rod on the bed. And also, you can see that the flow is a bit depressed downstream of the rod, so it can touch the bed if the flow is shallow. But basically, this is the range of depth and velocity conditions we can measure with this system. And you can see the design of the INRAE ruler here. So we will have 2 sliding rulers, a large, a broad one downstream, and a narrower one, the red one, upstream of the board. So they slide, so the operator can adjust them so that the tip of the rulers is at the free surface upstream and downstream of the board. And then here on this, using this ruler here, these graduations, we can measure the height of the surge. And so the velocity head, delta H, and then we can compute the flow velocity. So as I said, we didn't invent the system, but we worked several years to improve, to try to improve the practical use. So first, we validated and confirmed the velocity rating from Canadian colleagues. We also made a number of discharge comparisons and confirmed that usually we had discharge deviations smaller than 10%. except when the flow was too slow. So typically when the flow velocity is mainly lower than 20 centimeters per second, then we can have much larger discharge errors. We introduced a number of practical improvements, like setting a spirit level to help maintaining the system vertical. We also graduated the velocity results directly on the ruler, which may be interesting. And we replaced the O-ring fixations by magnets, which proves to be more convenient and more sustainable. Then we also introduced a method for computing the discharge and velocity uncertainties. And we also provided some tools, practical tools, especially spreadsheets for computing the discharge for those who don't use any other stream gauging software. And of course, now we also have this smartphone tool that Cedric will present a bit later on. So in a nutshell, the model and all the design is fully open source. We can provide all the files for 3D printing some pieces, for designing the ruler and so on. But it is also independently produced and marketed by a small company in France that sells the ruler. Okay, so about recent evolutions. Actually, a smart student during a field class told us that it would be convenient to have this red ruler graduated so that we can read the same distance head up that we can read at the bottom of the rod. When we use this initial method, we have to take the velocity head rod out of the water and to have the line of sight perpendicular so that we don't have a large parallax error. But actually, as the two sliding rulers have the same length, you can read directly the same length here. So we can read the water velocity head directly at the top of the system, which is actually more convenient. But if you have this new red ruler, please check that the two readings are consistent, because we had a few of them that were 1 or 2 millimeters too long or too short. So we had to replace some of them because they were not designed accurately enough. So please check this. And it's actually possible to replace your old ruler by a new one if you don't have this system, because the size it fits the same size and it's possible to replace it. Just the red ruler if needed. Okay, we have this spreadsheet, so it's not a very advanced software. It's just an Excel or LibreOffice spreadsheet. But we can print these parts for writing the measurement in the field. Then in the spreadsheet, we have the same form, and we have this kind of display of plots for examining the shape of the bottom, the depth, the velocity profile, the percentage of flow we have at each vertical, the extrapolated velocities near the edges if we have to tune the edge coefficients, for instance. And we added actually three uncertainty estimation methods. So it's maybe a bit disturbing to have different values for the discharge uncertainty, but then you can see the uncertainty of the uncertainty estimate. And you can choose the method you prefer. And we also display some uncertainty budget like this, so you can have a look at what are the dominating error sources in your discharge measurement if you wish to try to decrease the uncertainty. We also have this kind of field memento. We have updated it recently. This is just a recto verso sheet of paper that can be brought to the field just to remind some things not to be forgotten when measuring with the system. Perhaps you may have noticed that on our webpage we have released a frequently asked questions document. Feel free to have a look if you have some questions. Feel free to contact us still, of course, but there are a number of interesting informations in this document. You may also know this video tutorial that was done 1 or 2 years ago by Michael, and a new version will be produced in the coming month this year. Now, around the world, we are about nearly 400 users. 370 rulers have been released, mostly in France, but also in 20 other countries. And there are some bigger clusters, like in Haiti, Laos, PDR, or even in Canada, in British Columbia, for instance, due to some networks or projects. We have this web page and also a mailing list. Feel free to subscribe to receive some information when we update some tools or improve some tools. The main cluster of this pandemic is actually France, because the tool is now used by many river boards and other local stakeholders. And when they have technical sessions, when they meet in the field, sometimes they discover that that tool is used by some colleagues, and then they want to have their own. So we have in some valleys, in some river valleys in France, there are many rulers now. And here it's in Mayotte, an overseas French territory, but this is done in other regions as well. It may be interesting to measure on broad-crested weirs, like this broad-crested sill, concrete sill, where we have faster flow, very shallow flows, but a very flat and regular bed. So then the stream gauging ruler is quite efficient in this kind of situations that would be very detrimental to other current meters. We have done a number of training sessions where the rulers were included, especially in Normandy with Cedric, in Africa, in some parts of France, in Liverpool during the last River Flow Conference, for instance. We have this web page I already mentioned. Feel free to have a look. That is where I will release the slides and the video of this webinar. About references, we are sometimes asked which reference should be cited. So the main one is the paper we have published last year, which is open access. So anyone can have access to this paper. And in the supplementary materials, you can find the files for designing the ruler if you wish to make your own. And we also explain the uncertainty computation method. And we also presented about 100 discharge comparisons that are displayed here, confirming the plus minus 10% interval when the flow is fast enough, faster than 20 centimeters per second. Otherwise, the discharge deviations can be much higher. Of course, we can also rely on general references about the midsection method, especially the ISO 748 standard, but also a number of WMO, USGS, or other national agencies' documents. Now I will end this first part of the presentation by some glimpse at original projects using the stream gauging ruler. So first in France, the French Caving Federation developed a shortened version for their caving explorations, because sometimes they actually measure discharge underground in karstic systems. So they have this 60 centimeter version of the ruler, and they also developed an 3D printed this system for protecting the corners of the ruler, and to have some carrying system that is convenient for their explorations. Also, the Oxus expedition is a nice project based in England, but with three female explorers from 3 different countries, intending to prospect the sources of the Amu Darya or Oxus River, especially in Afghanistan. So they couldn't make it last summer, but they will try to measure the discharges of the tributaries they will meet in the upper Oxus, and they will bring two stream gauging rulers with them. And the last project is just starting in southwest France. It's a citizen science project for schools, college and lycée in France. And they have started to work with two schools. They have adapted the protocol for students, and those students are in charge of a river. They have to monitor the water quality, water quantity of their river, and they actually use the ruler for measuring discharge. And it seems that they do well with the system, even if the teacher didn't want them to use the smartphone tool. They stick to the paper and spreadsheet. But yeah, it's a very nice project. So sorry, I have finished with this first part of the presentation. And before leaving the floor to Cédric, I'm open to questions. If some of you have questions, feel free to raise your hand and open your mic. I will be happy to discuss. I don't know if there were some questions in the chat. Perhaps, Michael, did you see some questions or not? No? Okay, so I think I was crystal clear. This is good. Okay, so let's move to your presentation, Cédric, if you are ready.
Okay. I will just start just to make we do the presentation.
Yeah.
Okay, I think it's okay for the share of screen.
Yeah, it works.
Okay, so I'm Cédric. I'm working as river and one of the geomatic policy officer at Catacomb. CATER means Technical Coordination Unit for Water and River, Calvados-Horn-Manche. It's a non-profit organization involving counties of Calvados, Horn, and Manche, water agencies, and counties fishing federation from these three counties. Because we all have the aim to get some nice, good state of water course. So, okay, so I start to describe the stream gauging roller on YouTube. I was looking for an affordable tool to measure flow in a little river for model calibration. I wanted to use the Excel spreadsheet to get the flow ratio on each vertical component, but I don't laptop to bring it in the field. So at first I decide, you can see here, I decided to modify the Excel spreadsheet to make it usable on smartphone in a waterproof sleeve. I was especially interested by the ability to add intermediate vertical component to smooth too high flow ratio. This is why you can see there is some blank line between the different measure. It worked well, but was very error prone. It could be broken and filled with bad touch movement. And worse, it need, of course, an Office 3065 license, which wasn't in use in the state service in charge of environmental enforcement in France. As I had some experience building this field tool based on QField app, I gave me the challenge to bring the spreadsheet main feature in the QField interface. So this is a main component. Firstly, about the name, Curage stands for QField règle à jauger, translated as a QField stream gauging roller. In French, it sounds like curage, meaning dredging and digging up a riverbed. What we don't want, of course. It can be pronounced courage for those who are afraid by courage. Courage is built upon the top of four components. QGIS for the desktop environment, because it's the software I use usually. It's open source, cross-platform, extensible, very dynamic evolution, free. And locally, it's widely used by local authorities and all the people we are working with. So we are sure that they can use it easily. We also use QField, which is the equivalent software for tablet and smartphone environment, based also upon QGIS. And we use SQLite database with a Spatialite module enabled for storing and processing data. This is in the database that all the process is made, and where the spreadsheet formula were translated in a SQL language. So it's very easy to start. You just install QField from your platform app repository, or if you want, you can also load it from GitHub. After install, you can just keep this URL, and inside QField you can use import URL with this one. With a zip point at the end. And when you open, you will find all the project inside, because in fact, Courage is just a QField project which is organized to give you all working well, but it's a QGIS and QField project. So We use it because KeyField is designed to manage field data collection with a touch screen and bring perfect environment with differentiated geometry, input forms, pictures, and so on. So you can see here when you start, you just add a point because you can add a site, and after you can link many gauging measurement on the same site at different hours or date. You will find all the parameters that are in the spreadsheet. You can see here the start sessions time zone, water level, the starting position, river banks, coefficient. You have also some more. And you also can get some picture. You can have also some sketch over the picture, or create a sketch to represent some specific part of the station. And you can now you can see here you can manage with a reference flow. That could be one you calculated, you estimated, or which was one of your previous measurement. And you can make your first transect of measurement with this reference flow. And after you made all your transect, you can activate with this little button. And you will have the estimation about your flow, the measured flow, and not the estimated one. Here you can see that you have the different element of the spreadsheet, which is the distance on the roller, and you also have the percentage of the flow ratio. So here you can see if you have some vertical component that are over 10% or worst over 15%. And this is the plus because if you don't made enough vertical component, you can add more component. You just set another one with the correct position that you want, where you between the one that are too much higher. And when you add some vertical, it will compute directly and give you another flow rate for each vertical. So you can make the adjustment directly in the field just with a touch device in a waterproof sleeve. You don't need specific computer, works computer, or something like that. On the right, you don't see it, but on the screenshot, but you have also some little pin symbol, green, that give you the ability to keep the value from one measure to another. But it's very convenient if you need to make some lot of measurement with the same value, but use it carefully, because if you activate it, you can just keep the previous measure, and forget to make the new one. And after you made all the measure, you can go in a result layer, and you will see all the elements, the reference flow maybe you have, the water level, the time, and of course the gadget flow in a cubic meter and a liter per second, average speed, also weighted area, mean velocity. And actually, we have also included the Q plus uncertainty. The other one are not inside. You can export data to make it in the Excel spreadsheet, but inside you have the Q plus uncertainty that is included. And one of the interest also of this tool is that you can export a gauging report here with in which one you will see your picture, all the results, the detail of each vertical component. You will also see the color scheme, which is the same as the Excel spreadsheet. I mean, green for the value over or equal to 10%, and orange and yellow light range between 10 and 15%, and red over 15%. Well, if you all go well, you shouldn't have maybe a red line, but you can see it here if it's the result. And you have also a little map, and you can add your own logo on this report. So just in the field, you are ready to send the report to the people that need it. I used it some months ago, and I was able to send the report just before going out of the river. The report was in the mailbox. So we made Courage in 3 flavor, and you will see it when you load it on your phone or on your tablet. Courage Simple is a French language, and with in the background Hygiène Plan V2, which is for mainland France. We also a French language with OpenStreetMap for all the other territory that uses French speaking. And we have also with a base map OpenStreetMap translated in English. There is I saw some lack in translation for the English one. I see it when I made the switch and for the slide, but we will make some little improvement update to correct this little lack error. At the end, some other people chart displaying section like in the Excel spreadsheet with vertical flow, component, and flow ratio, and I would like also to see it. And also the ability to export data in a CSV format directly from the phone, because actually you need to transfer all the project on your desktop to export it with QGIS. You cannot do it directly from the phone. So after, when you export it in CSV, you can import in other software hydrometry. It probably could be done because there is now plugins framework introduced in QField with the last update. I just need to find time to learn 2 more programming languages because plugins are in Qt and JavaScript, and actually I'm only some skills in Python and SQL. So I need to learn some 2 more language, but I think it's doable. So at the end, and QField start to offer ability to connect external sensor to collect other data and X, Y, and Z position, but also speed as aim value. So it may open some opportunity to be a mobile platform for some other geometrical survey. Maybe in the future we can load other thing to. Thanks for your attention. So if you have some question, I'm open to every question you need.
Thank you, Cédric. I have not seen any question in the chat. I don't know if some of you have questions for Cédric about the smartphone tool. But already, Cédric, thanks again. A big thank you for having developed this tool. It's really convenient, really practical, and for long we wanted to develop such a tool, and we never were able to do it. And you just popped up and proposed to do it, and you find this Q-field solution that is, I think, very smart and very good idea. And
I
what
think the good thing is that it's wide open. Everything could be used by everyone. And if some people want to take it and improve it, it's open also to everyone. So we also can collaborate, for example, for including the chart or the CSV export. If somebody has some skills with this language, maybe we can collaborate to make this plugin for QField and makes this those improvement for Courage.
okay.
I saw some
Yeah,
questions.
there's a question for you, yeah, from Philip, right on this topic of Q-field, and perhaps you can read it, or Philip, feel free
Hi,
to.
can you hear me?
Yeah, sure.
Hi. Yeah, sorry to come in here. Might be interesting because I'm particularly interested in this Q-field component. So yeah, I'm the head of a global data center dealing with water quality data based at the Federal Institute of Hydrology in Germany. And I also coordinate the development and implementation of WMO's hydrological observing system, which has a very large ambition to basically connect various data providers and making all their hydrological data, observational data accessible. And there are various people also involved in contributing also at the European level. There's a lot of work being done on, let's say, fair water data infrastructure as part of the Horizon Europe Water for All initiative. And the colleagues in there, they have developed a QGIS plugin for SensorThings. SensorThings is one of the OGC APIs to exchange sensor data. And so this is already like in the making or part of QGIS. And we have started also a new project specifically on water quality, but with a similar approach that you have taken, to use QField as a field sampling app, so to say. So in water quality, people, similar as in hydrometry, they go out, well, they collect samples and so on. So we have started toying around with that. So I'm very happy to see your work, and would also be interested to follow up on that, to see whether we might be able to contribute or collaborate on that. So yeah, it's not necessarily straightforward. There are some issues with that, but our ambition there is really to have basically a QGIS open source system for people to manage all their water quality data, be it sensor data, be it field data, data coming from the labs. So a bit different topic than yours, but I see potential overlaps there. So it's really cool to see what you've already achieved.
It's nice because we can see a dynamic around the QGIS and QField use, so it's very nice to see it.
And it's always nice when in some projects water quality and water quantity can be interconnected, especially for this kind of partnerships or citizen science projects.
This is actually our motivation as well. We have quite some engagement also in Africa, especially on citizen science projects dealing with water quality through collaborations with Earthwatch or Freshwater Watch. That's an NGO, which is very active in many countries. And we just started this project with partners in Sierra Leone from the National Water Resources Management Authority, and trying to really get a better understanding of their actual needs in terms of data management and also how they do their work in the field. So I guess there's also a regional or a spatial overlap in terms of where we are active, and yeah, happy to follow up on that.
And so you were able to connect some external sensor to QField?
We haven't gone that far. So far, we've just kind of played a bit around with it, more in a sense. So for now, we just started basically digitizing the field sampling work.
Okay.
Like typically you have, or historically you have like manual sheets, paper sheets, when you go into the field to then note down these things. So digitizing this in a first step. Yeah, connecting sensors is a bit tricky because there's such a wide range of sensors. I've been in touch with a couple of projects or also developers who have developed their own like field apps, also in the context of citizen science, that are able to connect to certain selections of sensors, like water quality sensors in that sense, but they are for sure not too different with hydrometric sensors. But yeah, that's a quite difficult task because of the diversity of different sensors. So we haven't really spent too much time looking into a more generic approach on how to deal with this. We like handheld sensors, right? It's a bit of a different perspective when we talk about fixed install sensors, like telemetric systems. And this is where SensorThings comes in. So this is one of the activities we also want to pilot as part of this project. So there's a very cool open source software also implementing SensorThings called Frost. So that's server-based software to deal with time series data per se, but we have just extended it to also include all kinds of water quality data. And our idea there is to build like plugins so that different loggers or sensor data can be fed into the system like right away. And this then can be accessed from QGIS through the existing plugin. So people will be able to use like QGIS as the desktop client to access these different pieces of information, some coming from QField, and some from like a central Postgres database fed by this SensorThings API. This is still really early stage planning, but yeah, happy to further have any discussions around that.
Okay, great. Thanks for this information, Philip, and yeah, I'm sure we can follow up on this. I haven't seen other questions in the chat, so unless someone wants to ask a question, we can move on to Adrien's slides. So Adrien, I will share your slides.
Yes. Do you hear me?
Yeah.
Very well.
Great.
Yeah. Can you see the slide? Is it working?
Yes, I can, but it's not the right one. But
not this one?
Yeah, next one maybe. Yes. Ah, yes, it is. Sorry. Okay, that's it. Yeah. So it's in English. You translate. You make the translation. So hi everyone. I'm Adrien, and I work for the French Ministry of the Environment, and I work in a kind of agency, and we are in charge of the national network of gauging stations to measure the discharge. So the issue I will talk about is that we have more and more requests from local stakeholders who want to measure the discharge of small streams and in particular during low flows. And the requests, we have more and more requests, in particular since the drought, the severe drought of 2022, 3 years ago. And these local stakeholders, they have questions about issues about water management, water quantity management during summer, and also pollution due to wastewater or other pollutants. And they want to know the flow of their little rivers, and they ask us, can you measure the flow of this river? And we say, no, we can't, because we are in charge of the national network, and we cannot measure every single small river everywhere. So that's a problem, because they don't have many options for knowing the discharge. There is not a lot of private companies who can measure the discharge, and it's most of the time very expensive, because most of the time the company is far from the river, from the point of measurement, and it's costly to go and measure the flow and then go back, etc. So we were looking for a solution to get discharge measurement for small rivers that can be made by local stakeholders. So can you go to the next slide, please? The government. Yes, that's it. And there is a small illustrations from Jérôme, so you can appreciate it, I guess. So I will.
Sorry, chat, so I missed your. Sorry, I will focus now.
So the last year, in last summer, 2024, we made a kind of test with local stakeholders, and these people are in charge of a watershed of about 1,000 square kilometers that is located in the west part of France, between Brittany and Normandy. And okay, it's quite a flat area, close to the Mont Saint-Michel, a very famous monument. Okay. And within this watershed, the national gauging station network has 3 gauging stations. So this is, from our point of view, this is a well-instrumented watershed, because we have 3 stations. But from the point of view of the local stakeholders, this is not enough. Next, please. And for instance, they want to know the discharge of this small stream. It's about 80 square kilometers, the watershed. And even if it's surrounded by a hydrometric gauging station, they still have they are concerned about knowing exactly the flow of this river, because there is local issues of water quantity and quality, and quite important issues. So the name of this river is Minette, that means little cat. So that's why Jérôme put this illustration. So last year, at the beginning of the summer, we went. We had a field visit. We met with the local stakeholders, and we identified a proper river section for installing for hydrometric measurements. So we helped them installing a staff gauge and autonomous water level instrument, water level sensor. So the self powered, so it can measure water level continuously. And also, we taught them how to use the famous stream gauging ruler, and we identified with them a good river section for making the measurements. And then we asked them to make a measurement with the stream gauging ruler every 10 days during all the summer. Okay. And at the end of the summer, at the end of low flows, they came to our office with the data they collected, and we built with them a rating curve from the gauging they made with the ruler. So this is the stage discharge rating curve we obtained. It's not so bad from my point of view. So we get a relation between the stage that was measured continuously with the autonomous sensor and discharge that was measured from time to time with the ruler. And from this rating curve, we can then compute the discharge of this little stream during all the time of measurement, during all summertime, so all low flow period. And this is quite, I mean, to me, it's quite a good result, because now we can provide them, I mean, we can get a real discharge time series during all the summertime. And this discharge time series has been then saved in our national database. And the next step is we will ask the local stakeholders to repeat these measurements for, let's say, 3 to 5 years. And the purpose is, if they can do that, then we will try to build a relation between the let's say temporary gauging station with the measurements they made with the ruler, and we try to get a relation with the neighboring gauging station that pertain to the national gauging station network. So the purpose is, if we can get a good relation, then we can model the flow of this stream to extend the time series to the lifetime of the gauging station. So let's say it's about 30 years, and then we could estimate some statistics, low flow statistics for this river. So I did it just for last year, because for now we just have only 1 year of measurement for the smaller river, but it's just to show you. In blue, it's the discharge that was measured using the stream gauging ruler, and in orange, yellow, it's the discharge computed from the neighboring gauging stations using the relation I presented just before. And the interest of doing that is that I really think that we can get much more precise discharge values than in comparison if we just use a simulation without any measurement, because this is what most of the time local stakeholders will do, because when they do not have any solution for measuring, I mean, not too complicated solution for measuring the river discharge, they use simulations. And we have plenty of simulation models available, and one is very used in the part of France where I live and I work, is named the Simfen hydrological model, and it's a good model. But if you use only this model, you obtain the kind of brown curve, and the blue one is the discharge that have been measured. So there is quite strong errors of the simulation in particular in low flow. This is the added value of getting real measured measurements. So next. And this is just to illustrate the problems of using simulation. In the red curve is the error of the simulation compared to the measurements. So you can get 100, 200% of difference between the simulation and the measurements. This is just to illustrate that it's much better if you can implement a gauging station. Okay, so just to conclude, using the stream gauging ruler and autonomous sensor and all the solution we tried to develop, it can be a solution, and we will try to propose this option to local stakeholders who want to know the discharge of some of their streams they are in charge. It's not very expensive compared with let's say a standard gauging station. It's about 3,000 euros to implement this solution. The most expensive is the autonomous water level sensor. And it works because you can, it works if you have people who can go to the field quite often and make quite a lot of measurements, of discharge measurements. It's also, we also have limitations. It works if you can make a good discharge measurement with the stream gauging ruler. So it means you need a good river section, and in particular you need sufficient velocity. So if you have too low velocity, it will not work, as Jérôme presented before. And also you need not too rocky, not too rough bed, riverbed. So this is very important. And also it's necessary to make a measurement with, let's say, standard current meter, propeller or acoustic, just to check that the river section you identified is good, and that you get the same discharge measurement as the stream gauging ruler. Because sometimes we had the problem that you think that you have a good river section, you make a measurement with the stream gauging ruler, and it looks okay. But when you perform a measurement, a discharge measurement with a standard current meter, you find that, for instance, you have problems in flow at the bottom of the river, etc. So it's very important to compare with a more precise instrument. Okay, I think I'm done.
Yes, thanks, Adrien. This very nice feedback on this very nice project. I don't know if someone wants to ask a question on this project, but first I have to say that there are similar initiatives that are starting to develop in France, especially in Normandy, with Cédric and the regional office of the National Hydrological Service in Normandy. They based on this experience from Brittany, they started to develop similar projects. And as you said, Adrien, the biggest part of the cost comes from the water level sensor, right? I think that would be interesting for projects with lower budgets to look for even cheaper water level stations. And perhaps in some countries, it might be cheaper to have someone reading the staff gauge instead of a record. I think that in some countries in the south, that's what could be done. When there is already someone reading the staff gauge, he or she could measure the discharge with the ruler, for instance, or things like that.
I think you can. I think the cost of the sensor can be much lower. For I mean, it could be possible to develop much lower cost sensors.
Yeah.
German sensors, they're very expensive.
I know that WMO, there was some projects in cooperation with WMO to develop low-cost water level stations. Was a team from the US, I think, that developed something like that. Yeah. Okay, cool. No other questions? Yeah, I answered a question from Yegalem, but I didn't see other questions. So thanks again, Adrien. This last slide is also to thank many people who helped us during the development of this stream gauging ruler. We were from the beginning supported by the French Office for Biodiversity, OFB, and the National Hydrological Service of France, and many field hydrologists from the network helped us, especially in the beginning. Many of them made some velocity and discharge comparisons. That was really the basis of our first works and the validation of the velocity rating proposed by Robin Pike and colleagues. And thanks to the AAIS small company in France, we can direct people who would like to buy a ruler to them. There is no commercial agreement between us and them, but they do a good job. And as I said, the system is open source, so we can help anyone who would like to build it or have it built by another company. But many thanks to all these partners. I should also thank actually Robin Pike, because he actually helped us and discussed on our ruler model. Yes, so if there are no other questions or concluding comments from the audience, I don't see anything, so I think it's okay. I just conclude by thanking my colleagues, so Michael, Adrien, Cédric, and many others in our 3 groups. And I think that for once we will be able to finish on time, which is very rare actually. It's right 3:30. So with this, I will wrap up the session, and thank you all for listening and attending this webinar. Bye bye, everyone.
Thank you. Bye bye.
Thanks. Bye bye.
Bonnes vacances, Adrien.
Thank you. Bye bye.
Thanks. Bye bye. Have a good day or afternoon, depending on which time zone you are. And I will stop the recording.